Hello, my name is Alberto Mendoza, and this is my work called Influence of Gold Nanoparticles on the Schottky Barrier of Gold α-MoO3 heterojunction. This work aims to study the gold nanoparticle size dependence in the Schottky barrier height of the gold molybdenum-trioxide heterojunction. Schottky contact is formed by a semiconductor substrate and a metallic coating. In this work, the substrate is made of alpha-molybdenum-trioxide nanorods, synthesized by thermal oxidation at 500 degrees Celsius. And the metallic coating was made of gold nanoparticles dispersed on the substrate via DC-Sputtering. In order to vary the nanoparticle size, sputtered samples were subject to a calcination process at different temperatures. Characterizations were made to the substrate and to the calcinated samples, such as X-ray diffraction and scanning electron microscopy. In order to study the sample phase, morphology, and composition of all the samples at all its stages. And to inquire the Schottky barrier height, it is used X-ray photoelectron spectroscopy analysis, and as a result, different nanoparticle sizes were obtained with the proposed range of calcination temperatures, as well as different heights of the barrier. So, the Schottky barrier is a potential energy barrier that appears at the interface between a metal and a semiconductor, and induces a rectifying behavior in the material. The application of Schottky barrier devices is way too many, ranging from electronics to photocatalytic devices and power generators. So far, gold and alpha-molybdenum-trioxide heterojunction has been reported to be particularly useful in the photodegradation of pollutants and at ultraviolet range. So, by modifying and determining the Schottky barrier height will allow us to find new detection ranges and catalyst improvements. To do so, X-ray photoelectron spectroscopy analysis of the material can be used, and the Fermi level can be taken as a reference to do this. So the study and understanding of the Schottky barrier will allow us to elaborate very versatile devices, as well as to determine their capabilities and limitations in application. For the substrate synthesis, molybdenum foils were etched for 1.2 hours at hydrochloric acid and isothermally oxidated at 500 degrees Celsius for 5 hours. With this process of thermal oxidation, we obtain an array of alpha-molybdenum-trioxide intertwined nanorods on the surface of the samples. Then, the follow stage is to cover all the surface with a thin gold film, 5 nanometers of thick. We made this via sputtering for all films. After deposition, samples were calcined to promote nanoparticle nucleation and consolidation. This process was made on a temperature range from 400 and 500 degrees Celsius. As the calcination temperature increases, smaller is the nanoparticle size, but it is rounder. Distribution also changes with the temperature, as we can see in these pictures. To measure and study Schottky barrier on the interface, we use the following methodology to measure its height with XPS technique. So, it is known that for an isolated semiconductor, photoelectrons induced by X-rays can come from the edge of the valence band or below. For those that come from below are known as nuclear level electrons, and the energy required to eject those electrons is called nuclear level energy. When semiconductor is in contact with a metal, those Fermi level is different. So there is a bending on the semiconductor band near the interface. But despite this bending, parameters such as the band gap, for example, do not change. However, there are others that they do, such as the energy at the nucleus level, which in this case tends to be lower due to the band's bending, or the Schottky barrier, which does not exist in the semiconductor material away from the interface, but at the interface it does exist. There is a relationship that will always hold between these parameters, such as the following: the energy of the band gap plus the difference of the energy at the nucleus level and the edge of the valence band is equal to the energy at the nucleus level at the interface plus the Schottky barrier. So from this relation, we can obtain the value of the Schottky barrier with an XPS analysis. As results, we have X-ray diffraction results. Here we could see that all the changes in the samples throughout all the stages of the synthesis. In blue, we can see that molybdenum films after the chemical etching with hydrochloric acid. This process exposed the plane 002 of molybdenum, and it also increased its intensity. In cyan, there appear several planes corresponding to molybdenum trioxide in alpha phase. Later, once the sputtering and calcination are done, again we can appreciate a chemical change due to the presence of the planes for gold nanoparticles, which are more intense, as we can see, as the temperature of calcination is increased. Now, to analyze Schottky barrier height, it is necessary to acquire the parameters seen in methodology section. One of them is the energy of the valence band minimum, or valence band edge. We get this by analyzing the valence band of the substrate and the peak O2P to apply Kubelka-Moog method and find out this energy value, which is turned out to be 0.79 electron volts. Then the nuclear energy value is obtained by the doublet 3D of molybdenum because of the peak molybdenum 3D 3.5. It is created by nuclear level photoelectrons. Measuring these peaks before and after the gold coating gives us the nuclear energy before and after the gold coating, which turns out to be 235.93 and 235.84 respectively. With the initial nuclear energy and the valence band minimum, we can calculate the parameter EVZ. And considering a band gap of 3.58 electron volts, we can apply the relation mentioned before and obtain finally a Schottky barrier of 2.88 electron volts for the case of samples calcined at 500 degrees centigrade. So, in conclusion, with this project, we could be able to synthesize 4 gold molybdenum trioxide heterostructures, each one with different sizes of nanoparticles. It is seen that as the calcination temperature increases, the nanoparticle decrease in size, are more dispersed, and are more regular. In addition, through the XPS analysis, it is possible to determine the parameters of the metal semiconductor interface and thus calculate the Schottky barrier height, which is 2.88 electron volts for the case of samples calcined at 500 degrees centigrade. Thank you very much.